Thank you for having me and giving me the opportunity to present my work. I'm talking today about one-way Epr steering, and that is work that was done with quite a big bunch of people. And so I want to highlight the people that actually did the theory on this project, that are Travis Baker, Nathan Walk, and Howard Wiseman, and Jeff Pride was my supervisor. He supervised the experimental side of this project. So we know that entanglement is a key resource for quite a big bunch of quantum information protocols. And whenever we talk about entanglement, then we talk about the situation where we have a jointly prepared system, and we share this system between two observers, Alice and Bob, and they can perform a set of measurements on their side, and then in the end they compare their outcomes and say if they observed correlations or not. And this is something that was first described by Einstein, Podolsky, and Rosen in 1935, and hence the name EPR. And then a few years later, in the 50s, John Bell came up with a mathematical test which allows us to test for such correlations. And whenever we talk about a Bell test, we assume two black boxes, so we don't know anything about Alice, nor do we know anything about Bob, and we can compare that to different tests of non-locality and entanglement, and one of them is, for example, doing tomography or measuring an entanglement witness, and in that case we have full insight into what Alice and Bob are doing. And in a form of resources to go between these kind of different classes, we have to do something which we call trusting a party. And trusting a party is we make an assumption that we know what this party is doing. And in between these two different classes, we have EPR steering. And in EPR steering, Alice sits in a black box, and we know everything Bob is doing. And what you can see here, EPR steering was the first time experimentally demonstrated in 2010. And then there was a close detection loophole demonstration shortly after. And then long distance EPR steering in 2018. And you can see that happened so much earlier than the Bell demonstrations. And this is one of the reasons why EPR steering is so exciting, because it's much more robust to loss, robust to noise, and you can easier close detection loopholes. And in our experiment, we were wondering if when you have this EPR steering task, so you have the joint preparation, and then you share between Alice and Bob to find out if you had observed correlations, if you can do one-way EPR steering. And now I want to remind us all of how an EPR steering protocol looks in more detail. And so in the beginning, you share a state between Alice and Bob. But in this step, you do not know if they shared a bipartite state or if Alice has sent a single qubit state to Bob. And in the next step of the protocol, Bob performs a measurement on his part of the state, and then he's publicly announcing his measurement outcome. And because this knowledge is then available, Alice can pick the appropriate measurement setting, but we do not know what she did. All we know is her measurement outcome. And so we do not know if she tried to cheat on us or if it's a genuine measurement outcome. In the end, Bob takes both pieces of information, and then he's calculating a correlation function. And this correlation function is called the steering parameter. And if this steering parameter violates the classical bound, then we know the state they shared must have been entangled. And if it's below the classical bound, then we can't be sure. So in one-way EPR steering, we want to consider a scenario where we share such an entangled state between Alice and Bob. And here Alice is the steering party, so she's able to demonstrate, she's able to steer Bob's measurement outcomes. And then in the other scenario, now Bob is the steering party. He is not able to steer her state. And the answer to that, if that's possible, is obviously yes. And that was the first time experimentally demonstrated in 2012 by Roman Schnabel's group on continuous variables, and that is his main experimental result. So he has like two different steering regimes. One is two-way steering, so both parties can steer each other's state. And then he's adding a vacuum into Bob's arm, and that is the way how they create this one-way steerable regime. However, what we found is when you have these Gaussian states and you use Gaussian measurements, then it works perfectly fine, but as soon as you change the kind of measurements you perform on it, this is not one-way steerable then anymore. And so we were wondering, is it possible to find a states that are one-way steerable for arbitrary measurements? And that was theoretically demonstrated in 2014 by two independent groups. So one is Nicolas Brunner's group in Geneva, and the other one is Howard Weissman's group in Brisbane. And Nicolas Brunner showed they can do one-way EPR steering with a rather exotic class of state, and everyone who's doing experiments, no, this is the secret code word for never try to do that in an experiment because the parameter range is just incredibly hard. And then Howard Weissman showed it is possible to do it with a much easier class of states, so-called Werner states, but they only showed it for projective measurements. So that was, Nicolas' group was a step ahead of them in that sense. And then in 2015, well, we had a extension to POVMs. And then 2016, there were finally one-way EPR steering for 2 measurement settings per site, and then for arbitrary measurements, but in that case for Werner states. And that's the first part of the experimental work I want to talk about now. And so what we did in this experiment is we considered this following scenario. We have a symmetric or an asymmetric state rho. And this state is a Werner state, which is parametrized by the Werner parameter mu, which can range between 0 and 1. And if we have 1, then we have obviously a maximally entangled state. And to make this state one-way steerable, we used Nicolas Brunner's group's idea. We added a loss on one side. And if this loss fulfills this condition in regards to the Werner parameter, then we know it is a one-way steerable state that holds for POVMs. And so this is a scheme of the experiment. So we had a high heraldic efficiency Sagnac ring interferometer. So this is where we generate our state, and then we share it between Alice and Bob. Both have like their polarization analysis in each arm, and additionally, Bob has this loss P here, and this loss is the reason how we ended up with a one-way steerable state. And then we had a look at 2 different steering regimes. So the first one was obviously we want to show with this kind of source you create a state that is two-way steerable. And the second part is the state we created is one-way steerable, first for projective measurements, but also for POVMs. And so this is the result of our two-way steering. So we have the Werner parameter mu plotted against the loss P. And the state we created is somewhere in this white regime however, on the very far left, and I didn't plot it. And so we tested that state, and we tested against the steering inequality with 16 measurement settings. And we can see the Alice steering parameter and Bob steering parameter are above the classical bound. So that allows us to demonstrate steering. Then next we engineered a state that is one-way steerable for projective measurements. And we can see then Ella's steering parameter is still above the bound, so she can still demonstrate steering. However, Bob is below the classical bound. And then we engineered a state which should be one-way steerable for arbitrary measurements, POVMs. And again, we successfully demonstrated one-way EPR steering. So that was in 2016. And then 2018, we came up with new theory. And we thought, well, we have great Werner states. What about arbitrary states? So we wanted to kind of answer the question for once and for all, so arbitrary measurements and arbitrary states. And then, so we did the theory, and then we did the experiment, and the reason why we did the experiment, I will explain very shortly. So in the theory, we consider an arbitrary 2-qubit state, which you can just write in its canonical form like that here. And then the question was, what values for Bob's block vector and for the spin correlation matrix T do we have to consider that we could construct a local hidden state model for Alice? So when is the state steerable and when not? And then, of course, the second part of the question, how do we make this one steerable? And so we used again the concept of the loss depleted state. So we added again loss. And that's what you can see here. That's why you have Bob's heralding efficiency, which now depends on the loss you add into his arm. And that method gives us, again, a one-way steerable state. And so we found two steering inequalities, one for projective measurements and one for arbitrary POVMs. And then we tested our experimental data from 2016 against this new steering inequality. And what you can see here is the steering inequality, which is now a function of Bob's heralding efficiency, and the shaded blue area is just the uncertainty. And then we plotted our experimental result, and you can see the dot here is just on top of the bound, and within arrow it would be below the bound. And because we always assumed the state we generate is a Werner state, so we mapped it onto a Werner state. That is the star and an uncertainty. And you can see the rest of the little points here, they're for statistical reasons. And so we were not quite happy the way how it turned out, because it's not a conclusive answer. And that's the reason why we did the second experiment. And the second experiment, you can see here, uses a much more sophisticated photon source. And that is the main experimental data point. And again, we have these statistical information. And that is how the photon source looks like. It's a maximally entangled photon source. And you can add noise in a very controlled way in the second line. And then again, you bring the state together, you create it here, and you can share it between Alice and Bob. And again, in this experiment, we had a loss for our different steering regimes. And yeah, so this is just a characterization of the source, and you can see for the different Werner parameters which we generated, we had incredibly high fidelities with these Werner states. They're always in the regime of 99.something%. And we showed EPR steering by performing two different measurements. The first measurement is obviously you want to show Alice can demonstrate steering of Bob. And the second part is you use the tomography results on Bob's side together with his heralding efficiency, and then you test your new steering inequality and say, well, does it hold or not? And we did it again first for a fixed Werner parameter, where we are just varying Bob's heralding efficiency. And we see all the states we generated are above the classical bound. So all the states show here that Alice can demonstrate steering. And then on Bob's side, we see, two of the states which we generated, the ones with the red triangles here, they show no, it is not. You can't demonstrate steering. So these two data points here show Bob cannot not steer Alice's state. And then because we had this nice novel source, we did a second part of the experiment and we tuned the Werner parameters for different Werner states, and we can see also for that scenario. Our theory holds, and here it's the same again. We have two data points that are above the bound, and the red triangle here corresponds to this data point over here. So Alice can demonstrate steering, however Bob cannot demonstrate steering here. So it's a conclusive answer to the question if one-way EPR steering is possible. So, in conclusion, I think we successfully answered the question if one-way EPR steering is possible, and we did that for arbitrary measurements and arbitrary states. And so, well, this has obviously strong foundational impact, but also experimental impact, because we can see the importance of loss-depleted states, which is quite natural phenomenon in experiments when you try to do detection. And however, there still remains one open problem, and this is the tightness of our bound for POVMs. And I want to conclude my talk with a final slide. So what I'm doing now in my postdoc in Bristol, I was so lucky to inherit a really cool chip that was built by my colleagues, and their work was just published in September. And this is the biggest chip in the world currently, with 200 different components. And it is an arbitrary 2-qubit processor, so you can generate arbitrary 2-qubit states and perform arbitrary measurements with it. And we showed in this paper you can do at least 98 different 2-qubit operations, and you have a really good fidelity. And so we have a couple of different experiments lined up for this chip, but if anyone here in this room is after a cool collaboration or wants a platform which is ready to go and to test his or her theory, please feel free, come and talk to me. I'm sure we can have an interesting chat about that. Okay, thank you.
Hello, questions? Hello.
Hi, the experimentalist again. So at some point you mentioned the new source that made possible a second experiment. Could you give some details on the features of this new source?
Yeah. Okay, so the source is basically built up on following Chris Deschamps' scheme. That is the source he used for the Bell inequality paper. And so the first part here is it's the singlet state source, and you can pump in superposition this lower part, and depending on how much of the pump you send into this lower part, that's how much you decrease your Werner parameter. And then, so we went away from the Sagnac scheme to this scheme, because using beam displacers, they have a higher extinction, and because of that, you get a higher quality state. Yeah.
Okay, thanks.
More questions? No? Okay, let's think again. Okay, sorry, here, just one.
Am I right that in the sorry, am I right that in the theoretical the one-way steering demonstration for 2 qubit states and arbitrary POVMs, that was the latest result, right?
Yeah, that one.
Right. And did you like? Are you thinking at all of like higher dimensional things, like for steering?
What do you mean by higher?
Like instead of 2 qubits, 2 qubits. I don't know.
Oh, going.
Yeah.
Oh.
Well, okay. I guess that be included.
Yeah.
Yeah. Okay. I mean, if you can do it with qubits. You can.
So maybe in the sense of maybe Howard Wiseman thinks about starting a collaboration with someone.
Okay.
I don't think Jeff is going to do that.
Right. I mean, not
So-
experiment. I guess the theory side is what I was wondering about.
Yeah.
Yeah.
No, I don't know if they're going to extend that work. Sorry.
Okay, more questions? So, okay, let's think again, Sabine.